In this video, we'll take a look at pathway determination. So we're going to focus exclusively on the SN1, SN2, E1, or E2 pathways. So in a general sense, we're going to have to look at a few factors that dictate if a substitution pathway is most likely or if an elimination pathway is more likely. So generally speaking, these substitution reactions are nucleophilic substitutions, which means that we must have a nucleophile in our reagents or a part of the reaction. And in elimination, this is acid-base chemistry in which a beta hydrogen is removed from the alkyl halide from your substrate, and you will get an alkene product in this elimination. So essentially, if you're looking for a substitution reaction, you need a nucleophile, and if you're looking for an elimination reaction, you will need a base. Here we have a chart that summarizes the key factors in determining which pathway is most preferred, SN1, SN2, E1, or E2 specifically. So it's broken up into several different parts here. So first of all, we'll talk about the substrate. So our substrate is either going to be primary, secondary, tertiary. It could also be benzylic or allylic, and we will touch on those a little bit in our specific examples, but they still fall under these general pretenses of primary, secondary, or tertiary. So remember, a primary alkyl halide is something that it has one carbon bound at the carbon of interest. So for instance, this would be a primary alkyl halide with a chlorine, specifically alkyl chloride, where this carbon is the one that's going to be the reactive center, because this carbon is bound to the leaving group, the chlorine in this case, and it is bound to just one carbon. It is substituted by one carbon. There are two hydrogens there, so this is primary. And secondary is similar. Now instead of having one carbon bound at that center, you will have two. So here's our secondary position with only one hydrogen remaining and these two methyl groups, so two carbon substituents. And then tertiary is similar, and there is a third substitution. So tertiary center would look like this, where there's now no hydrogens at this position. There is only carbon. There are only these methyl groups bound to that center. Okay. So now that's defining all of those. Now let's get into some of the specifics of the reagents that we're talking about. So here, this first column is a strong nucleophile and a strong base. So when this happens in a primary alkyl halide, this is always going to be a SN2 pathway. That will be the preferred pathway. Now, some reagents that would give this, that are both a strong nucleophile and a strong base, is something like hydroxide. Sodium hydroxide is both a good base and a good nucleophile. There are many others, but this is a good example as any to begin with. Then, if you do the same thing with secondary, this will be an E2 pathway. And again, this could be NaOH, or there are some others, but NaOH is a good example. It's both a good nucleophile and a good base. So the reason that elimination will predominate now when we get to a secondary substrate as opposed to primary is because, in general, acid-base chemistry is faster than substitution. So if there are things that promote a acid-base reaction, like an elimination pathway, that will predominate if it's given the chance, which is the case in a secondary and higher substitution substrates, because it's very difficult now for the nucleophile to approach this carbon to undergo a substitution reaction. It's a lot easier for the hydroxide to approach a hydrogen and remove that hydrogen as an elimination product. So because of that, that explains why we have SN2 with our primary center, same reagent, and then for our secondary center, we would get E2. So again, this type of reaction would be with NaOH or a similar strong nucleophile and strong base. And then tertiary, this follows the same idea that we just talked about with elimination. This is going to be E2. And again, this could be with something like NaOH. This will be E2, just to reiterate the point, because it's extremely difficult now for the NaOH to approach this carbon because of all the methyl groups that prevent the approach. They're blocking it in a sterically demanding fashion. Okay, moving on to the next column, we have let's say we have a strong nucleophile, but it's a weak base. So if this is the case, then we are going to get a SN2 pathway. Something like this would be, let's stick with our ionic state. So let's call this the sodium, I think this is called thiolate, not positive on the NaSH name, but the difference here is sulfur is much more weakly basic compared to oxygen, because as we recall in the periodic table, our trend for basic strength, it increases as we move up and to the right on the periodic table. So therefore sulfur is lower on the periodic table, so it is a worse base. It's a weaker base compared to oxygen. And if we do the same thing now, moving down to our secondary position, this is still going to be SN2 pathway, because it is this is a strong nucleophile and a weak base. So it cannot act as a base, the sulfur, to undergo an elimination pathway like we saw in the first column. So it's only going to undergo SN2. Then when we get to the tertiary center, like we just talked about in the first column, the tertiary center cannot undergo SN2. So this will not be SN2 in this pathway. The only thing that is available to us is SN1 or E1. And again, the reason for that is the secondary, the E2 elimination pathway is not available to us because the sulfur will not function as a base. So the only thing we have available to us is SN1 or E1, and it's also possible that this would be no reaction. It will simply depend on the specific case. In this case with NaSH, you would primarily get SN1 as your product. Okay, moving on to our next column. This is strong bases but terrible nucleophiles. So this is going to be something like a T-butoxide or something that prevents the nucleophilic attack. So here we have a primary center. If we have a strong base and a weak nucleophile, this is going to be E2. Because the nucleophile, since it's such a weak nucleophile, it would be unable to approach in a nucleophilic manner to give us the SN1 product. SN2 product. So here, something like T-butoxide would be excellent. This is a very strong base, but a terrible nucleophile, again, because of the size. And then secondary, it's going to be the same thing, give you E2, and tertiary will also give you E2. And again, we can use T-butoxide to accomplish this as our reagent for either substrate case. Okay. Now, if all of these cases don't apply, these first three columns don't apply to your specific case, then you need to pay special attention to the solvent. Now, the solvent can be either polar aprotic or polar protic, and this will dictate which pathway is preferred. So SN2 pathways prefer polar aprotic solvents. So in a polar aprotic solvent, you'll get SN2 with a primary and a secondary substrate. And again, when you have a tertiary substrate, you will not get any SN2 under any situation. So this is only going to be SN1 or E1 if we have a tertiary substrate. And then on the other hand, polar protic solvents prefer SN1 and E1 type mechanisms. So in this case, with a primary alkyl halide and a polar protic solvent, we will still get SN2 since it's primary, but as soon as we get to secondary, it's now going to switch to SN1 and E1 because the steric hindrance and the polar aprotic nature of the solvent will dictate that it will undergo that mechanism. So what are some polar aprotic and polar protic solvents? So a prototypical example of polar aprotic is acetone. The aprotic part just means that it cannot have hydrogen bonding. And remember, to have hydrogen bonding, you need to have an oxygen or nitrogen or fluorine bound to a hydrogen that is then in proximity to a hydrogen that's bound to an oxygen, nitrogen, or fluorine. We don't have that possibility with acetone, so this is great. I can put that down for all of these specific cases here. Okay, now a polar protic solvent can have hydrogen bonding, so something like water or an alcohol, let's just keep it as ethanol here for this example. These would be polar aprotic solvents, stuff like this. So now you can use this table, and I encourage you to, when you first begin to assess these problems, because it will begin to ingrain that pattern recognition that you need to be able to do these types of reactions very quickly and efficiently. So definitely use this as a tool, but after time, you're going to have to be able to recognize what is a nucleophile and what is a base very quickly. So we'll go into that now. Okay, so the table is only useful if you can determine what is a strong nucleophile and what is a strong base, and when you have those ambiguous cases where you have characteristics of both a nucleophile and a base. So what I'm going to give you next is an extremely simplified view of what determines nucleophilic and basic strength, but it works very, very well for a large majority of the reagents. So as general rules, these are pretty good factors to go by. So that's what I'll give you as your beginning guide. It can become more specific and refined as we move along. So here, though, we're looking at what's the difference between a nucleophile and a base, and really it all has to do with size primarily. So, and two factors that make a nucleophile a stronger nucleophile is if the reactive center is a large atom, but the molecule itself is a small molecule. So to understand this, you have to know the difference between an atom and a molecule. Recall that an atom is simply an element or a single element that it constitutes that atom, whereas a molecule is a structure where multiple atoms are bound together. So for instance, an atom would be like an oxygen or a nitrogen, but a molecule would be like water, which as we know is H2O, which has 3 atoms, 2 hydrogens and 1 oxygen. So following this idea, a really good nucleophile is something like pH3, where we have a phosphorus that is a large atom. It is in the 3rd row, and the molecule is small because it's substituted with 3 hydrogen atoms, which are all very small. So this would be an excellent nucleophile because the phosphorus, the reactive center, is a large atom, but the molecule itself is extremely small. Now, if you look at the base, it's the opposite. So the reactive center is a small atom that prefers basic nature, and if the molecule is a large molecule, then that will support basic behavior. And these go hand in hand, right? So the more likely something is to be a base, the less likely it is to be a nucleophile by these rules. So something that is a large atom and a small molecule is what we would consider to be a strong nucleophile, but a weak base. So I should include that here. This would be a strong nucleophile, but a weak base, right? So if we look then at our chart, going back here, this would be the first, not the first column, it would be the second column where we have a strong nucleophile and a weak base. The pH3 would fit in this category as well, as does NaSH that I used as our first example. Now, on the other hand, bases have small atoms at the reactive center, but the molecule themselves are large. So this is why T-butoxide is usually the first example given, because the reactive center is the oxygen. This is in the 2nd row. This is a small atom, but the molecule is very large because of all these methyl groups. This T-butyl group makes it very bulky, makes it difficult to function as a nucleophile, so therefore it will be a base. So this now would be a strong base and a weak nucleophile, right? These are kind of the unambiguous cases, the clear cases. Like this would be our 3rd column here, where we have a strong base, but it's a very weak nucleophile, something like T-butoxide. However, there are cases in which you have characteristics of both. And in this case, there has to be other things in the reaction conditions or the reaction mixture that dictate what is the molecule going to be, so, or how it's going to function. So let's consider ethoxide. It's a good example. Okay, so here let's look at this. So we have oxygen is our reactive center. That's a relatively small atom. So oxygen equals small atom. okay? But the molecule itself is also pretty small. This ethyl group that is the substituent here is relatively small, right? So this is a small molecule. Okay, so this, in essence, is a small atom reactive center and a small molecule. If we look at our rules, small molecule suggests nucleophile, small atom suggests base. So this has basic properties and nucleophilic properties. So this is a basic properties and nucleophilic properties. So this molecule is a strong nucleophile and a strong base. Right? So now if we go back to our chart, this is the first column where we have strong nucleophile and strong bases. So what is going to dictate the type of pathway that you undergo is almost entirely due to the substrate and or the solvent if that becomes relevant in the particular situation. So this is exactly how you should go about looking at the problems. You'll identify your substrate, determine if it's primary, secondary, or tertiary. Then you will look at your reagents and determine if it's a nucleophile or a base. And then you can use your chart to assess the most likely pathway based on all of those conditions. All right, now for the remainder of the video, we're going to take a look at several examples to tie this all together. So just like I just finished saying, we're going to look at the substrate first. So let's make a short list here. So we make observations about the substrate, and then about the reagents, and then if necessary, the solvent. That will be last. Okay, so in this case, our substrate is primary. So we have a primary alkyl halide. Right? Again, we're looking at this reactive center, the center that is bound to the halide, the leaving group. It is only substituted by one carbon, so this is a primary alkyl halide. The reagent, we have a small atom, the oxygen, and a large molecule. Right? So that is a base. So this is a strong base, but a weak nucleophile because it's so large, so weak nucleophile, right? So now in this case, this becomes clear what the pathway will be. We don't have to consider the solvent, but the solvent is polar protic, which in this case would just confuse us, which is why it's usually, I say it's unnecessary to look at the solvent unless all of the other factors still make it unclear as to what the pathway is. So now let's put this all together. We have a primary alkyl halide and a strong base, weak nucleophile. So let's look at our chart here. Primary alkyl halide, strong base, weak nucleophile. This is going to be E2 almost unanimously with no substitution product. Okay, so let's take a look at how we would draw this mechanistically, just to put some other ideas together as well while we're at it. So here is the beta, down here, here's the beta hydrogen. So what's going to happen is this functions as a base. This will remove the beta hydrogen, and then when that happens, it will form the alkene simultaneously, and then the chlorine will leave, and you will get the alkene product. So your final product, putting this together now, is this, and then you also lose the T-butyl alcohol and Cl minus as your leaving group, right? So here, this is just our E2 product, the alkene. We have no substitution or unimolecular process, no SN1 or E1. All right, moving along. Here we have another question, and our substrate is tertiary. This is a tertiary alkyl halide. So right away, that tells us that it's not SN2 because we have a tertiary center. Secondly, our reagent is not particularly helpful in any case, right? Because if we look, our oxygen is a small atom. This molecule is a relatively small molecule. So this would be suggestive of base or a nucleophile. But due to the fact that it's not charged, this would make it makes it weak at both features. So this, in this case, is neither a strong nucleophile or a strong base. This is just weak at both. And if you take a look at the chart, oops, weak nucleophile. You take a look at the chart, you'll see nothing about weak base or weak nucleophile. And the reason for that is when we have a case like this, this is simply going to be our solvent. So this is a polar protic solvent, right? Polar protic solvent, because you can have hydrogen bonding with itself, water can. So we have a tertiary alkyl halide, polar protic solvent. The reagents don't tell us any information really in this case. So this has to be SN1 and E1. Primarily SN1, but you're going to get some of the E1 product as well. So if we look at this again, mechanistically, the first step in any elimination or any unimolecular process is the removal of the leaving group. That will give us this carbocation. And now the water can function as either a base or a nucleophile. If it's a base, it'll remove that proton that I just drew. So let's draw that process. Remove this hydrogen, form this alkene, which is your E1 product. This is E1. Or the alternatively, let's draw this in a different color. You can have water function as a nucleophile in which you create this bond at that carbon, the carbocation. So this would make this molecule. And then you'll get a proton transfer at the very end, which will remove that proton. So this can happen with another molecule of water to act as a base to remove that proton, or depending on your style, you can just draw it to freely move. It doesn't really matter usually. So this is going to give us the SN1 product, which is the alcohol. Right? Okay, so again, this one was relatively straightforward because we have a tertiary center, which already favors SN1E1 because of the stability of the carbocation intermediate. This is a tertiary center, which is very favored in terms of the SN1 and E1 pathway. And then after that, it's just a matter of drawing the products in the correct manner. Okay, so let's move right along. Okay, this one's a little bit more ambiguous because our substrate is secondary. This is a secondary alpha halide, which means it could be anything, right? It could be any pathway. So the pathway that's going to be preferred will be dictated entirely by the reagent. So we have a nitrogen is our reactive center. That is a small atom, which suggests base. And NH2, it's only substituted by hydrogen, so that makes it a small molecule, which is suggestive of a nucleophile. So putting these two pieces together, this would say that it is both a strong base and a strong nucleophile. But since it's secondary and it's a strong base, this is going to be E2. Right? We can look at the chart to confirm this. But remember the explanation. All right, so here we have a strong nucleophile, strong base, secondary, E2. The explanation for this is simply that acid-base reactions are typically faster than substitution. So here in this case, we do have a base and we have a secondary position which hinders the substitution pathway. So the elimination pathway is going to be the only one that we see in this case. So now we have to look for our beta hydrogen. This is the alpha position. There's two beta positions. They will yield the same product, so I'll only draw one. And here's the mechanism. So you have NH2 as your reactive species, negatively charged. That's why it's sodium amide with the counter ion of sodium. Then this is going to function as your base, pull off this proton, form the carbon-carbon double bond, and then cleave the iodine simultaneously. This is all a concerted mechanism in E2. And what we get is this cyclohexene. And then ammonia is a byproduct and the I minus, right? And since there was sodium floating around, there's sodium floating around here as well, but I didn't draw it there, so just to be consistent, I'll leave it off here. But this would usually crash out as sodium iodide salt. All right, here we have another question. So let's look at our substrate. We have a primary alkyl halide. So we know that that is suggestive of SN2 because it's primary, most likely to undergo a substitution pathway. We look at the reagents. We have a small atom, the oxygen, and a small molecule because it's just an ethyl group. It's not substituted heavily by like a TBO group or something. So this is both a strong nucleophile and a strong base. But now, in this case, we have a primary alkyl halide instead of secondary like was the previous case. So because of that, this is suggestive of SN2 because of the primary nature of the alkyl halide. So again, let's look at the mechanism in determining the product here. Right, so here's our alkyl halide, and then let's draw the nucleophile. This is this ethoxide molecule here. This oxygen will attack the carbon, this reactive center, and then we'll kick out the leaving group onto the bromine, or the electrons onto the bromine, which is the leaving group, and then this will give us our ether, which is the substituted product, the SN2 product. Always count your carbons and make sure you added the molecule correctly. So here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then 7 and 8 are a part of this ethoxide group that was bound, and we are all good. Our atoms are all conserved. So this is SN2, and we have Br minus as a byproduct. Again, with the sodium floating around, this is probably sodium bromide as the byproduct because the counter ion will balance the charges. All right, moving along, we have another question here. So we have the same substrate, or similar substrate in this case, with now a new reagent. So here, this is a secondary alkyl halide. Okay, and again, this is similar to water. This isn't a strong nucleophile or a strong base. This is just a solvent. So this is going to be a polar protic solvent. So this is suggestive of SN1 and E1 because we don't have a strong base or a strong nucleophile. So this is going to undergo a carbocation formation. When that happens, you always have to be weary of carbocations because rearrangements can occur. So in this case, we will have a rearrangement product. So the first step, as always in a unimolecular pathway, is the loss of the leaving group to form the carbocation, which is this one. And now we can have a hydride shift, where this hydrogen here can shift, and then you can create a tertiary carbocation. Right? And this is more stable than the secondary that we originally formed. So this is going to quickly interconverge. It's going to quickly go from this secondary carbocation to the tertiary as soon as this forms. And when that happens, now you have a reactive center, again, just like you would have had before, but it's the more stabilized one, so the activation energy would be lower to get to this intermediate. Now you can have your alcohol function as a base or a nucleophile. to give you the E1 or SN1 product, depending on what you do. So we'll start with the SN1 product. This will attack the carbon that has a positive charge, and then there'll be a proton transfer, which I've already shown that step, so I'm just going to say minus proton transfer, and then that will give you the SN1 product after the proton transfer takes place. So this is the product, right? We have our methyl groups at that position as well, and then the OCH3. Again, we lose the H because of the proton transfer step that I'm not drawing here, but I'm just describing with words and illustrating with just that, the text there. And now we can have the E1 product as well. And in this case, there's several. Well, there's two. So there's this hydrogen here that can be removed and form that alkene, or there's this hydrogen here, which is equivalent to the hydrogen, the other methyl hydrogen. So that's why there's only two products. So I'll draw two reagents to show the different products. So if this were to function as a base, it would remove that and go there. That would give us this product. Or let's draw this in a different color. Or this can remove this proton and form this alkene, which would be this one. And this is more stable. These are both E1 products. This one's more stable because the alkene is more substituted. So this would be this would be formed in higher yield than this product. But in this case, you're going to get such a mixture, it's going to be hard to tell what's the major product. So I would draw them all if this was a question, especially since you're getting the substitution pathway as well. That is going to drive your yield down for any one of these particular pathways. All right, here we have another question. Again, let's start with the substrate. So this is a secondary alkyl halide. So again, that's somewhat ambiguous, makes it difficult to narrow down what pathway is preferred. This is H2SO4. This is a strong acid. So this doesn't fit under our nucleophile or base at all. It also could have hydrogen bonding with itself, but that's not critical here in this case. It's more important that it's a strong acid. So this is going to favor E1. This is a special case in which you have an acid that is non-nucleophilic, and this is due to the size of the acid. So I'll draw the structure for you to illustrate this point. So this is a very strong acid, and the conjugate base, where you remove this proton and have a negative charge on this oxygen, is a terrible nucleophile. It's a terrible nucleophile because this is so bulky, right? It's so bulky, it makes it very difficult for that oxygen to attack a carbocation, for instance, which would be in this case. In addition, the oxygen can delocalize that negative charge to these other two oxygens, which again promotes that it's not going to react because it's stabilized by resonance. So this is going to be E1 then by necessity because there's no other options. It can't be nucleophilic substitution. So mechanistically, the leaving group will leave, form the carbocation, and notice this is the same species that we created earlier, so we will get the hydride shift as well, just like we did in the last case. And this gives us a tertiary center. With the hydrogen is now here and the tertiary carbocation. And now what happens at this point is we get spontaneous cleavage of the hydrogen. So this will cleave and we get our product now. At the same time, this one could leave, but again, this gives us a less substituted product, which is less likely to form because it is not as stable. And the reason we get this spontaneous cleavage is because we're in an acidic environment. So it's favored now to have H plus that's lost, because if H plus is lost, we're already in acid, so that's okay. You could also make the argument that Br minus is floating around from our leaving group step, the very first step, so this could be promoted by the Br minus. I've seen it both ways, and I think it'd be acceptable to include either one. But the reality is you're getting the E1 products and only the E1 products, no substitution products. All right, here we have another question. So in this case, we have a secondary alkyl halide. Again, this is somewhat ambiguous, so we'll have to look at our substrate or reagents very carefully. So we have a phosphorus that's a large atom, and the molecule is small because there's just hydrogens, right? This is also a polar aprotic solvent, no hydrogen bonding. So, oops, a protic, yep, putting that all together. This is then going to be a strong nucleophile, but a weak base, which is then SN2. Even though we have a secondary center, we have a really good nucleophile. It's not that basic, so it's not going to get any of the E2 product. So let's look now at our pathway here, mechanistically. So we have our reactive center is this secondary alkyl halide, and we have a methyl group here that has some chirality. And now we have our phosphorus, which is our reactive reagent, the nucleophile. This will attack the carbon bearing the leaving group, and then this bromine will leave. Again, this is concerted. So this nucleophile has to approach from the backside, which means that the stereochemistry is going to invert, which always happens in SN2. So the product is going to have where the wedge was, it's now going to be a dash to invert the stereochemistry, and then the phosphorus is bound there. The phosphorus now has a positive charge because we're using this lone pair to bind there. So check out the video on formal charge if you're confused about this, but the phosphorus will have a positive charge, and then the Br minus will be floating around to balance your charges. That was in your leaving group there. And then the methyl group remains unchanged. The only reason that this stereochemistry matters is because it has been unchanged by this reaction. So you get only this molecule, not the one where this methyl group would invert or something like that. That would be a very different type of reaction. All right. Let's move on to another question. Using the same substrate in this case. So again, secondary alkyl halide. So that doesn't give us much information. The molecule is a small molecule and a small atom or reagent. A small molecule. So this is a strong base and a strong nucleophile, right? So because it is a secondary alkyl halide, this is going to be E2 because the elimination pathway is preferred when it can happen. So that's what's going to happen in this case, since we have both a good nucleophile and a good base. Now let's take a look at the mechanism. So remember, in E2, we need an anti-hydrogen. So in this case, we have two beta hydrogens that are anti, right? This one is anti because it's like trans, is similar to anti. So we have that position, and at the same time, we have these hydrogens, which are achiral. So you can have free rotation, and one of them is definitely going to be anti at any given time. So we're going to get two products then. Let's look at the first one here. Doesn't matter what you pick first. I'll take this hydrogen first. Like I said, it doesn't matter. And then the bromine cleaves. So again, remove the beta hydrogen, form the alkene, and then the leaving group leaves. In this case, bromine. This will remove the chirality of the methyl group here, because this is now an sp2 center. It's not sp3, so it cannot be chiral. It only has 3 substituents, and that is going to be one of the E2 products. Now the other product is where you remove that other beta hydrogen. again with NH2. Remove the one that's anti. In this case, we can't tell by the way that I've drawn it, so you pick one, doesn't matter. Then you form this alkene, and then the bromine leaves. So what this forms now, it's a very different product, which has the double bond here. You retain the chirality at this methyl group. And again, in both cases, you have Br minus as a leaving group, and ammonia as a byproduct, since you used it as a base to grab that proton. So if you were going to assess which one of these is going to be the major product, it's probably going to be this one because it is tri-substituted alkene compared to a di-substituted alkene. But I would imagine that you get a non-negligible amount of both of them. So I would include both as possible products if this were a test question or homework question. Okay, let's do another one. All right, so here we have two reactive centers. They're both secondary. So I will just say 2 secondary for the 2 positions that are secondary alkyl halides. We have this is a good nucleophile and a weak base because it is a small molecule and a large atom. So that is an excellent nucleophile, so strong nucleophile, and a weak base. Okay, and this is also a polar aprotic solvent. So putting all this stuff together, this is definitely going to be SN2. Again, even though that we have a secondary center, that's all right because we have polar aprotic that's suggestive of SN2, and we have a terrible base, again, suggestive of SN2. So we're going to get SN2. Now, we are told that we have excess of this species, this sodium thiolate, so that means that it's going to have an SN2 pathway on both of those centers. So now the question is, which one reacts first? In this case, it doesn't really matter based on the way that the question is asked. Since you have excess, it's going to react at both centers, and it's not critical which one reacts first. But if the question were slightly different, the kinetics would matter. So bromine is a much better leaving group than chlorine, because remember, leaving group strength is due to the base strength. So if you have a weaker base, that's a stronger leaving group or a better leaving group. So the bromine is the better leaving group of these two. So more than likely, the sulfur, the thiol sulfur is going to attack the bromine first and then get this intermediate. Again, this is SN2, so you get inversion at that center, right? Just like this. And then again, we lost Br, so I'll just draw minus Br minus as byproduct. And then we'll get another attack at the chloride center now. Like this. Again, minus Cl minus as our leaving group. And then we get our di-substituted final product. This one here. Again, the stereochemistry inverts at both centers because it's an SN2 reaction at both centers. Okay, moving on to the next question. Okay, so here we've seen this reagent several times now. We have a good nucleophile and a good base. So this is a small atom, large, oops, not large, small atom, small molecule, which is indicative of both a strong nucleophile and a strong base. Here we have a secondary alkyl halide. So this is E2. Again, because based on a reagent, it could be either. So since we have a strong base, secondary center, that's always going to be E2. So since it's E2, we need to have an anti-hydrogen. Again, a beta position hydrogen that is in the anti-orientation for this mechanism to work. So there's only one such hydrogen in this case. It's this hydrogen here that I just drew. This hydrogen is not anti, it is syn, as in it's cis to the chloride. It has to be anti to the leaving group, so you're only going to get one product in which this beta hydrogen is removed. So mechanistically, we get this hydrogen removed, formation of the alkene, cleavage of the leaving group, the chloride, and then this gives us the alkene product. Like so. Again, we lose the chirality at that methyl group there because the sp3 center has now become sp2. We also have our chloride as a leaving group and ammonia again, our byproducts. And this is an E2 product. And you only get one product, like I said, because the other beta hydrogen is not in the anti orientation. Okay, let's move on to another problem. Okay, so here we have a primary alkyl halide, suggestive of SN2 right away. Here we have, again, we have a small atom and a small molecule. So this is both a strong nucleophile and a strong base. So I'm abbreviating this process now a bit because I've shown it several times. So look at the previous questions if you're still confused as how this is determined. But this is both the strong nucleophile and a strong base. The fact that it's primary, this is going to be SN2. Okay, so we get our SN2 product, which means that we would get inversion of our stereocenter if that mattered. In this case, it does not matter because this hydrogen, or this carbon, the reactive center, is not chiral because there are those two hydrogens bound at that position. So here then, what's going to happen is simply a SN2 substitution, nucleophilic substitution reaction like this, to form an amine. Oops, missed a carbon there, right? Don't forget we're binding to this carbon. So the structure that I've drawn there is not correct. It is, in fact, this one, right? Where we have formed a carbon-nitrogen bond, and then it has bound to its two hydrogens that were a part of the original molecule. And this is a SN2 reaction. We also get chloride as a leaving group, which will be floating around in solution as well. Since we had sodium, since this was really sodium amide, I would say that it's going to be table salt, NaCl, that's really around in solution, but you know, that's fine. You should definitely include those counter ions as they are, even though they may not be reactive in the, or mechanistic function, they're still included in the reaction mixture. Okay, moving on, let's do a few more questions. We look at this one here. We have a secondary alkyl halide, and this is neither a good base or a good nucleophile because it has no charge. It's just an alcohol. It's similar to water, so this is probably a solvent, and this is polar protic. So this is suggestive of SN1 and E1. Okay, so now this question is critical to understand because, again, it has rearrangements that are possible, but this is a perhaps more challenging rearrangement to notice. So here in the first step of any unimolecular process, it's always cleavage of the leaving group. So you get the T-butyl group and this secondary carbocation that forms. Now there's no hydrogen at the adjacent carbon, but there is a methyl. So what you get is a methyl shift, which gives you the following product. Right, with a carbocation in the tertiary center now instead of a secondary center. So that is a favorable process that I've drawn there. So now what happens is you get your SN1 or E1 pathway, depending on which one you want to draw. So here, this will be our SN1 pathway. So we have our alcohol, which is ethanol in this case, drinking alcohol. And this will attack the carbocation position. Again, there's going to be a proton transfer that I'm not going to draw just for time. We've already seen them in a couple other cases. So we have proton transfer, and we get the ether as the final product. Which is this one here. Again, count your carbons and make sure that everything's all balanced out, but it should be. Okay, so then we can get the E1 product. So by the way, this is our SN1 product. Okay, now we can get the E1 product, which there are a few. There's only two actually in this case, so the alcohol can function as a base now and remove two different protons. This one will be the primary removal because it gives you a tetrasubstituted alkene, which is quite stable. That gives us this product. Or you can remove this hydrogen, which gives you now a disubstituted alkene, which that product looks like this. So these are the two products that you get. They're both E1. Again, among the E1, the tetrasubstituted alkene is by far the more likely, but you're going to get a significant mixture of all of these products, which again is why E1 and SN1 aren't the most useful reactions, because you get often a lot of different products that may not be the one you're after. Okay, so let's look at another question. All right, so here we have a secondary alkyl halide again. Now, KOH, this is both a strong nucleophile and a strong base. So secondary, this is most likely E2. Okay, now it will be E2, but there's one thing that's important to mention before I get into the mechanism of this here, is we have some acid-base chemistry that may be going on before the reaction begins. So here we have OH minus, and then we have this alcohol. So this proton is somewhat acidic, right? So you can have this acid-base reaction occur before anything else occurs, which will give you water as a byproduct, and then the alkoxide. Now the alkoxide and OH minus are about equivalent in terms of base strength. So this is either way, one of these will function as a base. It won't function as a nucleophile. So in this case, it doesn't really matter that much, but you should pay attention to it, because in some cases this equilibrium might not be so equal. So in this case, this is an extremely balanced equilibrium, because the pKa of alcohols is about 16, pKa of water is about 16. So this is basically an even shift. So it's difficult to say whether the hydroxide or the alkoxide is going to be predominant in solution, but in either case, they're both going to function as a base. So this is still going to be E2. So now, then if you look at the mechanism, there's only going to be one product, and this is due to the nature of the molecule here. So there's only one beta hydrogen. Well, there's technically three, but they're all at the same position that I just drew. This beta position has no hydrogens because it's completely substituted by the methyl groups. So you're only going to get the one product in which either molecule, the hydroxide or the alkoxide, will remove one of those protons. It doesn't matter which. I'm drawing both here, but I'll draw the mechanism just with the hydroxide. So here is your mechanism, and then this gives you the alkene, again, like so. This is the E2. And water is a byproduct from the acid-base reaction, and that is it. Okay, moving on to the next question. Getting pretty close to the end here, but I wanted to be as complete as possible so you guys can do these questions like they're piece of cake. All right, so here we have a tertiary alkyl halide. Again, this is a strong acid, so this is going to be E1. Again, it can't be SN1 because sulfuric acid is so bulky and non-nucleophilic, so it's not going to undergo any SN1 type of chemistry. So mechanistically, we again form our carbocation, the leaving group leaves spontaneously, and you get a tertiary center here. No rearrangements possible in this molecule because of the nature of the carbocation. There is no ability for it to be different. So you could get two possible products. Again, it kind of is up to your preference whether a hydrogen leaves on its own or the iodine functions as a base and removes it. Kind of this is your preference. I would definitely ask your teacher which they prefer, but I've seen both. So it's kind of up to you as far as I'm concerned. So then here we have this as one product, and then this hydrogen can move and give you the other option. Now in this case, this is tri-substituted. These are both E1 products. This is going to be favored because it's tri-substituted, more substitute alkene, it's more stable. So that is by far going to be your major product or in higher yield. Okay, moving on to another one. Okay, so here we have a relatively large atom. Bromine is a large atom, and this molecule is small. So you would suggest that this is a strong nucleophile, weak base. You'd be right. That's suggestive of SN2. All right, here's the secondary position. We didn't talk about this first, but it's secondary alkyl halide. So you would suggest that this is SN2. Problem with this, though, is the leaving group. Fluoride is a horrible leaving group. Terrible leaving group. And the reason is because HF is a weak acid. pKa, I don't know, somewhere around 5. Look that up to be sure, but it's somewhere about 5. It's not strongly acidic, which means that the conjugate base, F minus, is pretty strong base. Comparatively, you know, if you compare it to like HCl, again, I don't have these numbers memorized offhand, but HCl is a really strong acid, so its pKa is definitely negative. Let's say -2. Again, I'm not positive on the numbers, but something like that. Now, here's something that's important to keep in mind. You might say 5 and -2, that's only a 7 difference, right? It doesn't seem like that much. But pKa is a log scale. So the difference between the strength here is 10 to the 7. That's 10 million. So that means that HCl is 10 million times more acidic than HF, which means that F minus is 10 million times more strongly basic than Cl minus, which also means that F minus is 10 million times worse of a leaving group. So that long spiel is telling us that this fluorine is such a bad leaving group that it doesn't matter about all this stuff. This is no reaction. You're not going to get anything useful out of this condition. So the point that I'm making with this question is that always keep in mind some of the other stuff that we talked about. You have to have a good leaving group before any of this even matters, right? Before you're trying to determine if it's E1, E2, SN1, SN2, you need to have a good leaving group or none of this will take place and you're simply going to get no reaction. And you'll see questions like this on your exam. So definitely just be comfortable with recognizing that as a part of what is going on in any given question. All right, here is our last question today. Sorry for how long this video ended up being, but hopefully it has been extremely useful for you guys. So here we don't have a halide again. So this isn't a good leaving group. So right away I can tell you that this is going to be no reaction as far as E1, SN1, etc. There's going to be none of these, but something could happen here. And this could be thrown on your exam just to keep you on your toes. And what could happen is you have a lot of acidic protons and you have a base. So you could get a bunch of exchangeable proton transfers. So for instance, there are 2 major equilibriums that you can draw. And this question would only be useful if you knew the pKa's of everything involved, which you don't need to for this question to just be answered, but it would make it more useful as which equilibrium is going to be most favored. So by the way, this is equilibrium since it's acid-base chemistry, and you shouldn't draw it as a full arrow like that. You should see, well here, I'll just redraw it so we don't get confused. It's half arrows is equilibrium, not this. This will get you -1 or something on your exam if it was free response. So always draw it like this. That is the correct way of representing equilibrium. So now we have our O-. This can remove this proton. And then we would get this. And again, there's potassium around, so this would be a potassium counterbalance there, and then water. And then the other reaction is the one that we've already talked about with the other alcohol that's in the solution. So you'd get this. So again, these pKa's are all going to be pretty close. I'm not positive about the cyclopentanol. That could be a little bit different due to the nature of the cyclic structure. But again, you wouldn't be able to tell which equilibrium is going to be favored unless you had those pKa values. So if this was simply the question is predict the pathway, you would just say no reaction except for these possible exchangeable proton transfers that I've drawn out here. So that is all I have for this video. Hopefully you found it helpful. And if you have any ideas for future videos or any questions, please feel free to leave them down in the comment section below, and I'll get to it as soon as I can. But with that, I hope you all have a good day, and I'll see you in the next video.